Okay, here we go. So Harshita, please, the floor is yours.
Yes. Are you able to see the slides?
Yes, perfectly.
Am I sharing the desktop or
No,
the
we see the slides in full screen.
in full screen mode? Okay. Just a second. So, sorry. So, okay, great. Yeah. So thank you so much, Stefan, for inviting me, and I'm so glad to be here presenting this work. As I was mentioning to Stefan, I've worked on this area of automatic differentiation and floating point error estimation during my postdoc, and also I had a project that was funded by the LDRD at Lawrence Livermore. Since then, I have moved away a little bit to other areas of high performance computing, but this is still a very topic that's very dear to my heart. So I do try to keep in touch with what's happening in the field. So with that, I'll get started. I slightly changed uh, the title from error estimation for floating point operations to quantifying floating point errors for approximate computing via automatic differentiation. So, and understanding where precision can be safely relaxed and why should we even be doing such a thing, right? What is the motivation for studying this? I do see some messages on chat. Feel free to unmute yourself and ask
It was
questions.
just me with the
Okay.
workshop indicator.
Oh, okay, okay, great, great. Yeah, if you have questions, feel free to unmute at any time. I do hope to have enough time for Q&A at the end, but so let's get started. So why are we looking into floating point errors and what is the motivation for this work? So here is a plot that's showing the microprocessor trends over the years. You might have all seen these kind of plots. And we know that until the early 2000s, the computer performance was primarily driven by clock frequency, and that was attributed to Moore's law, doubling of transistors, and Dennard scaling. But that free lunch is over, right? It's been done for almost a decade now. So single-threaded performance have stagnated, Dennard scaling has ended, and the Moore's law is kind of slowing down. So all this has sparked researchers both in industry and academia to look at different computing paradigms and what kind of next generation innovations can we do. So propelling the computer performance beyond the limits of Moore's law would require rethinking the technologies from materials to devices to circuits and architecture. And this was a report a few years ago, um, a report to the president of the United States stating that if we want to ensure long-term leadership in semiconductors, innovative new technologies like these quantum, neuromorphic, and approximate computing are necessary, and these are considered moonshot computer architecture technologies. So therefore, approximate computing is an important area, and that needs due attention. And the way we anticipate the next phase of computing advances to be like a heterogeneous system, which involves combination of different resources, each suitable for a specific kind of task. And future heterogeneous platform might involve a diverse set of architectures from all the way from multi-core CPUs to approximate computing hardware and quantum chips. And since not all high performance computing applications need the same kind of accuracy all the time, and not all parts of the program contribute to the output accuracy equally, this kind of gives us an opportunity to leverage approximate computing for regions that can tolerate it while utilizing the precise hardware for regions that need those high precision to achieve overall performance gains while maintaining the accuracy because we all care about that. So, the general idea of trading accuracy for performance has been around for a long time in scientific code. So, this is an example of Barnset algorithm n-body simulation, where the far fields are approximated by their center of mass. And the selective approximation makes the simulation go faster, and the algorithmic complexity goes from O(n) squared to O(n) log n. There are other examples like the inexact Newton methods for finding the roots of a function. So this is like an iterative process of obtaining the solution. The solving the linear equation at each stage can be very expensive if the number of unknowns is large, and need not be, and there's an exact method approximately solves the equation in the initial iteration, where it doesn't matter so much because we are anyway far from the solution. And when we get close to the solution, then we use high precision ones. So these are examples of practical HPC applications, high performance computing applications that use some kind of approximations to improve performance. So just to step back, what is approximate computing? Let's consider an example here. This is a code, and this is transformed. I'm sorry. This is the transformation, and the transformation is called loop perforation. And what it does is it takes the loops in the program and transforms them so that they execute fewer iterations by selectively skipping iterations. So, what do we think is going on here? Would it give any good results? Some people might say the program will run faster, consume less energy, but you ask any scientific researchers or HPC computing folks, they'll say that this program is going to give you the wrong results, and we're never going to use something like this. So, but that's actually not true. What it ends up doing, it gives a different results. And what we are really interested in knowing is how different is that result going to be? And if we can bound how different that result is going to be, then perhaps we can use these techniques and make the code faster without losing much accuracy. Right. So approximate computing is based on this intuitive observation that performing exact computation requires high amount of resources. Allowing some selective approximation can provide disproportionate gains in efficiency. And approximate computing leverages the presence of error-tolerant code regions to trade off accuracy for performance gains. So, approximate computing can be realized both in hardware and software, and researchers in academia and industry have been working on approximate hardware for some time, and here are some examples of that. These could be adder multiplier, where the system drops fixed number of mantissa bits. JPEG and ray tracing use this kind of could leverage a lot of benefit with this. Then there is voltage scaling, which reduces the energy consumption at the expense of introducing errors such as read upsets. Then approximate memory uses memory access skipping and reducing the rate of DRAM refreshes. This has been shown to do well in video applications. Approximate GPUs attempt to reduce the number of control flow and memory divergence. So these are like techniques that are done in the hardware. We might be more familiar with the techniques that are done in the literature for software techniques. There is obviously mixed precision. Well, I'll talk about that in more detail, and that's going to be the main topic of today's talk. Which is about, the hardware supports multiple levels of precision, and mixed precision involves using different precisions in the code to improve performance. And we really care about accuracy at that point. Then there is code perforation, which you just saw an example where we drop certain loop iterations Function memoization identifies common patterns in data parallel programs and uses an approximate kernel for the detected patterns. Then function substitution replaces functions in the program with an approximate version of it, something like a neural network or surrogate model. And then relaxed synchronization, where for applications that have locks and synchronizations, they can remove some of them, but can also introduce data races. So, have to be done very carefully. So the focus of today's talk will be on mixed precision. So HPC applications, high-performance computing applications, scientific applications use floating point arithmetic operations extensively. Like the computer architecture supports multiple levels of precision. The standard IEEE floating point choices are single, double, quad, and half. And now we even have like 8-bit and tensor cores and things like that. So the choice of floating point precision determines the magnitude of the rounding error in the computation. So, although we would love to use higher precision to improve the overall accuracy of the program, it usually results in an increase in application runtime and energy consumption, memory pressure, and interconnect use. So, the alternative is to use lower precision. So, but then why don't people use lower precision? It can reduce runtime and things like that, memory pressure, but people then don't tend to use it because it can impact the accuracy of the simulation. What use is it if the simulation produces wrong results, right? So programmers usually resort to the safer option of uniformly applying high precision throughout the program to ensure accuracy at the expense of performance. But one thing to note is that not all applications require high precision everywhere in the program. So ideally, applications should use lowest precision necessary to achieve the required accuracy to take advantage of performance and energy benefits that the lower precision hardware can provide. So, when we look at the top 500 list, this list was released in 2022, and the top of the list, Frontier, at that time, right now it's El Capitan from Lawrence Livermore National Lab. At that time, on Frontier, which is an Oak Ridge machine, made the exaflop, and was very interesting to me at that point was Frontier demonstrated 1.1 exaflop in high precision, but it demonstrated 7.9 exaflops on mixed precision calculation of HBL benchmark, which is a mixed precision version. So clearly showcases that, what can be achieved if you use the mixed precision correctly in a application. So what is mixed precision, right? To go a little more into detail, mixed precision is using lower precision arithmetic when possible to improve performance and reduce the energy usage, and using high precision arithmetic wherever it's necessary to maintain accuracy. Unfortunately, it's not very easy to develop mixed precision versions of large code bases manually because it not only requires extensive knowledge of the numerical behavior of the algorithm, but also requires an understanding of, subtle details regarding floating point round-off errors, and this becomes really infeasible for large-scale programs with multiple modules. And I also want to take a step back and think about what was this is an example of the Patriot missile failure. And what I want to say here is that relaxing precision, while we talk about it very frequently, this is an example of why we should be extremely careful. What happened in this case was in 1991 during the Gulf War, an American Patriot missile failed to intercept an incoming Iraqi Scud missile. And the Scud struck the barracks, and a lot of lives were lost, and several people were injured. And a report that came out later attributed this to computer arithmetic error. So what was happening was that this time was measured in by the system clock in 1/10 of a second, and was multiplied by 1/10 to convert it into seconds. So 1/10 in the computer format is represented like this, a non-terminating sequence of bits. And computers can't really store infinite bits. In this case, was truncated to 24 bits after the decimal point, resulting in a small truncation error that you see there. But when you multiply this truncation error with a large number, it brings down to like a really significant error. And what had happened was that Patriot had been up for 800 hours or so, resulting in an error of 0.34 seconds. And a Scud can travel more than half a kilometer in that time, far enough for the Patriot to miss it, leading to this catastrophic event. So these are some of the examples, and I'm sure you have heard of other examples where uh, not taking into account the impact of floating point errors could result in devastating scenarios. So, so I've talked about approximate computing. So will we ever use it? So approximate computing, we've noticed that has been used in several areas where applications can inherently tolerate inaccurate computation, like image processing. A few erroneous pixels don't really affect the human recognition of an image. Or in the case of search, the ranking of the search results beyond the first 10 don't need to be accurate. But how about high performance computing? The thing is, blindly applying these techniques like mixed precision or any other approximate computing technique uniformly throughout the code can result in incorrect properties. And that's primarily the reason why HPC folks are very hesitant to use it in scientific codes. And many times, in order to find approximations that give significant performance gains, it requires a very in-depth knowledge of the application, and also requires considerable modification of the code. So if we really want to use these techniques to gain performance, especially given that the hardware is moving towards yeah, enabling these techniques by default, like the tensor cores and all, we must be able to ensure accuracy, ensure efficiency, and ensure ease of use. And this was a project that I'd led a couple of years ago, where we developed certain frameworks that enable the use of approximate computing and HPC algorithms, use of pragmas for leveraging LLVM compiler and runtime support. We also needed to use automatic approaches to reason about the impact of accuracy. And we used HPC benchmarks for all that. We have several works and papers on different aspects. I encourage you to go to my Scholar page and take a look at that. But in this talk, I will only focus on the accuracy aspect, since that's the topic of this talk. Um, So as I was saying, it was in the process of writing these proposals on approximate computing, and I was very cognizant of the fact that people in scientific computing are very hesitant to use approximate computing because they produce non-reproducible results and wrong answers. So if we really want to gain acceptance, we must be able to quantify, like approximate computing can result in different output. We would really like to know how approximate computing affects the program. For that, we need to estimate the output error. Applying approximate computing throughout the code can result in violation of correctness. So we need to identify are the regions that are amenable to approximations, and not all techniques can be applied. How can we easily test out some of these common techniques? So we worked on, this was done by my postdoc at that time, who's a staff now, Dinos Paraserius, developing a benchmark suite that consisted of kernels and mini apps that were widely used in HPC domain. It had a test driver to automate the test and analysis process. And we evaluated several mixed precision methods on these kernels. And the vision being that these benchmark suite would evolve into standard HPC benchmarks for evaluating computing, different approximate computing techniques. Here we primarily focused on mixed precision, but it could be extended. And he had developed quite a bit of drivers and things like that to enable folks to easily use it. And what's the idea? So these mini apps represent real application. You can test some of these techniques on these mini apps, and then you can extrapolate it to larger apps, which is always a concern, but at least it can give you a sense of, I've tried this out on this mini benchmark, and now moving on to larger application, how does it change? Or and before putting in all that work to evaluate it on large scale applications. This is I'll skip these in the interest of time, but these are basically results from that benchmark suite on various application mini apps. So what we quickly realized when we developed that benchmark suite is that manually identifying manually identifying different kernels and different approximate techniques is just not possible. We need like automated techniques to find these. As I mentioned, we need these techniques to determine the impact of using the approximation on the code. And also, obviously, how much performance benefits do we get? But our primary focus was determining the impact of using approximations in the code. Like I mentioned, you cannot use it throughout the code. You need to identify what are the approximable region that can be relaxed. It could be variables, it could be array components, it could be functions, things like that. So the fundamental goal here was to understand the impact of errors introduced by approximate computing techniques so that we can develop programs that execute faster, better integrity, and correctness of results. And we used automatic differentiation as one of the techniques for that work. And I will also talk about another technique developed by another postdoc of mine. But let's get into the floating point error estimation tools that are out there. There have been many efforts to automate the process in various ways. One is on automatically discovering unstable floating point execution. And accuracy improving transformations based on a database of rewrite rules. Then there is dynamic automated search-based approaches. These techniques evaluate and execute different mixed precision configurations of the program to identify the best configuration that satisfies the error threshold. The main drawback of this approach is that the state space is quite large to explore, and it's exponential in the number of variables or kernels, and exploring even a subset is very time intensive. Then there are various rigorous static analysis approaches using interval and affine arithmetic or Taylor series approximation to analyze the stability and provide rigorous bounds. But unfortunately, they don't scale very well and therefore haven't been applied to any HPC workloads. Then there's algorithmic differentiation has been used to study the impact of floating point errors. So here are several works on AD and in some form or the other used to study the impact of floating point error. So automatic differentiation has been used for sensitivity analysis in general, and this goes back to a long time ago. Langlois proposed a method called SINA, which used AD to compute a correction term for elementary rounding errors to improve the accuracy. Gafar had used AD for bit width optimization on FPGAs, and there have been other works that combined interval analysis with algorithmic differentiation for significance analysis, and then using it to do control flow instability due to round-off errors and things like that. So the work we did was along similar lines, but slightly different. You'll see in the following slides, we made it, all these works had never been done on any HPC code, or there was no, not integrated very well with it was mostly theoretical analysis kind of work, which was pretty cool. But we wanted to implement it on HPC kernels and study their behavior in real life. So in this book, I'll talk about the tool we developed to automatically identify different variables that require high precision to ensure correctness. And then we use mixed precision analysis to achieve a desired output accuracy to improve the performance. So the question we have is, we're interested really knowing how does the output change with respect to the errors in the variables. So we view a program as a function of inputs and intermediate variables to compute the output. So in our error prediction model, we use the first order Taylor series approximation of the program around the input to compute error estimates. So let's say let X be an input or an intermediate variable in the program and Y be the output. Then we know that the error in Y is F dash of A times the error in the input X. So this can be extended to consider the output Y as a function of multiple inputs, and generalizing it, we get the total differential delta Y is the sum of partial differentials. And the key point here is that we can use automatic differentiation to obtain the partial derivative F dash of A, specifically the reverse mode of automatic differentiation. And for this work at that time, we had used Quantifying AD tool for this purpose. I'm assuming folks here are familiar with, somewhat familiar with AD and AD tools. So I will, directly go into how we ended up using it. To identify a set of variables that can be changed to lower precision without violating a given error threshold, we began evaluating the output error due to lowering the precision at every dynamic instance of each variable. So let's say a variable is in a for loop, is used in a for loop. So at every dynamic instance of the variable, so every for loop or every time the variable is changed, we evaluate the output error due to lowering the precision. And then we aggregate the output error estimates at the assignment level as well as the source variable and function level. And then we use this as a basis of our mixed precision allocation and use a greedy approach to create a mixed precision configuration. Then the variables are stored in increasing order of their contribution to the final output. And then finally, the variables are assigned to lower precision if converting them does not violate an error threshold. So we use this principle to generate a sensitivity profile of the program for round-off error. So the absolute error due to rounding off is the magnitude of that variable times the machine epsilon. So if P being the number of bits in the mantissa, P is 11 for half precision, 23 for single precision, 52 for double precision. If we reduce the precision, the rounding error will be magnitude X, magnitude times the machine epsilon. And the error metric, E, to capture the sensitivity of the output with respect to the round of errors of any variable in the program. So we create this kind of sensitivity profile for every single variable at every dynamic instance. And then we sort them out, and then we iteratively, in a greedy way, add each variable to the list of lower precision variables if it doesn't violate the accuracy constraint. And for this, we use the reverse mode of automatic differentiation to compute the partial derivatives of all the variables with respect to the output. Here's an example of how it looks. So we evaluated it on HPCCG. It's a CG mini application that's part of Montevo benchmark suite. It's a conjugate gradient benchmark. And I believe we used, I forget what size we used for the problem. But the report that we get out of that tool looks kind of like this. So the code, the tool is called Adapt. And it highlights regions in green that can be in higher precision, and in red those critical sections that need to be the ones that are in green is in lower precision, and the critical sections that need high precision are shown in red. And we find that because we're doing this at every dynamic instance, so we can look at across the iteration how it looks. We found that the initial iterations are critical for accuracy. And this plot kind of shows the critical variables across different iterations. And this could be the problem we're looking at and the problem size and things like that. And the results indicate that after the initial 20 iterations, the error in R, the residual, is below 10 to the power of minus 10. And and this gave us the information that we could have things in higher precision in the initial iteration, and then perform lower precision at arithmetic in the later iterations. And this gave a speed up of 1.1x without any change in the results. So this was pretty interesting. Then we moved on to evaluating it on a kind of a larger mini app. We used Adapt on a mini app called Lulish, which is a shock hydrodynamics program developed at Lawrence Livermore. And this is showing the call graph at the function level, highlighting which functions need to be in higher precision. The reds are the ones that need to be in higher precision, are very critical. And what we found was that the time step variable is just used to advance the simulation, and therefore doesn't need to be in that accurate to like the last significant bit. So we use this profile to guide the development of the mixed precision version for a CUDA implementation of Lulish. While we did this for non-CUDA version, we could extrapolate. This is just giving you insight about the application. You can use this insight to develop the mixed precision version of CUDA, and the mixed precision was within the error threshold that we had specified of 1 to the power of 10 to the power of minus 11, and gave a speed up of 1.2x. The routines were, if you're interested, routines were called calc LM characteristic length, and these were, important parts of the simulation and taking up too much runtime. And that's why when we optimized it, we got a performance benefit of 1.2x. So we've evaluated on several smaller benchmarks, comparing with other techniques at that time, like the state-of-the-art techniques at that time. What I want to highlight is that our approach was able to, so here you can see the actual speed up that we got. It's able to identify mixed precision version of the configuration that satisfies the error threshold. So the user sets the error threshold, and the actual error threshold is less than the set error threshold, and still get a speed up of significant speed up. So we extended this work. This was the work done by Garima and by Dinat with Vasil. Yeah, and it's called Chef FP and was published at IPDP as the previous work. Adapt was published at SC, I believe, 18 or something. This work, we took it further to make it seamless. Instead of the user having to annotate things and use an external AD tool in a very cumbersome manner, and this work looked at how to do it in a very seamless way. So as I mentioned, this is going to be using AD to get the derivatives. So the right side, so this source transformation of AD happens automatically in the tool. And you can see on the right, the source transformation for a square root becomes, the 2 times x. And for Chef FP, the AD plugin built for Clang is called CLAD, and CLAD provides source level information. And this is the way we have made it automatic. And we'll go into the little more detail about the architecture of Chef FP. Okay, too many animations, but let's see. Okay, so the code the user writes is parsed by Clang. And when Clang detects calls to, let's say, estimate errors, it passes the control to CLAD. And then this is the CLAD part. The CLAD starts generating the derivatives of the function, but keeps a lookout for assignments. And anytime when the control is sent to Chef FP through CLAD for these assignment statements, Chef FP then captures more information about the source code, such as the name of the variables, and then gets the derivative of the variables in question and passes that information to the error model. So it collects all that information and the derivatives and goes to the error model. Here you have flexibility to write your own error model. So we had written our one version of the error model similar to what you saw for the adapt paper. The error model outputs the error through code generated, and we emit the estimation code itself, which then CLAD, this is the code, which then the CLAD would put it into the code that is generated as part of the derivative code. And it finally produces the derivative with the error estimation code and gets compiled by Clang. So how do we use this tool? Let's say you have a kernel function defined. You can then include CLAD header, and you also specify the error model you want to use. There are some standard ones that are part of Chef FP now. So CLAD estimate error tells CLAD that you want to run Chef FP on this function. And the Chef FP then produces the derivatives. This is how the generated code would look like. It produces the derivative, calls the error model, and then sums them up to produce the final results. So final error. Then you can execute them with the necessary arguments, and it will print out the mixed precision error report. So this kind of generates that report for that can be used to do mixed precision analysis. So to identify the set of variables that can be changed to lower precision, we evaluate by lowering the precision of every dynamic instance of the variable, similar to adapt, but it's all done automatically now with very less overhead. We use this as a basis of and aggregate the errors over all the dynamic instances of the variable. And then we use this as the basis of mixed precision allocation, the same approach of greedy approach. And there are a couple of variants of this algorithm in the paper. And here's the table, very similar to the adapt one, but it makes it very seamless to integrate it with any application now. Want to highlight is that the same thing. So it's able to estimate the output error and be very close to the actual error. And for a given threshold, it's able to find quite a bit of speed up as well. It also performs better than adapt. I don't know if we have the results for that here, but basically with adapt there was a huge overhead involved in doing the error analysis, but with that the error analysis overhead is significantly lesser, and then we're able to do the same kind of analysis and obtain significant speed up too. There is this other work I'm not sure. Do we have? Maybe I shouldn't. Yeah, there was this other work done by another postdoc. I won't go into the details here, but it's basically about designing error-bounded approximate computing technique kernels. It was accepted at CISC at that time, and the framework kind of has the terminology for designing error-bounded approximate kernels. I would encourage you to take a look at that paper if interested in that work. The technique was called QDOT, and we show that we are able to identify regions of the array that can be done in lower precision while satisfying error approximation, user-specified approximation tolerance, and have a very good bound. And here we are showing that the bound we predict is very much closer to what we actually get. It's pretty interesting work. And we did it for the dot product. And there are other works on designing frameworks to make it easy for folks to use the approximate computing techniques. And it's very extensive work with lots of different ways to basically makes it easy for someone to specify, I want to use this approximate computing technique. And there we have like perforation memoization, function memoization, and things like that. So it can be very easy to incorporate this in a kernel and study the impact in that way too, without having the user having to write down or transform the code to do all those things. So I want to conclude and give some time to the audience to ask questions. So just to summarize, we've done a bunch of work in the approximate computing world, and many of it was focused on mixed precision analysis. And we designed methods to understand the impact of the errors that approximate computing techniques introduce. We used automatic differentiation, and there is also another work by the two postdocs on using uncertainty quantification to do these kind of sensitivity analysis as well for floating point perturbations. And then we incorporated all this to guide the process of applying an approximate computing technique. And here with Garima and Vassal, we have this paper on incorporating this as part of compilers too. So with that, I want to conclude my talk and am open to questions.
Thank you very much. Excellent talk. Thank you very much, Harshitha. Are there any questions to Harshitha?
I want to ask if there are no questions. What are some of the challenges you folks are facing in terms of applying, let's say, mixed precision or reduced precision in your codes, and how are you guys handling all that? Oh, I see a hand
Okay,
raised.
please go ahead.
Hey, thank you for the presentation. So there's two kind of issues that just our cursory look at auto differentiation is seen. So we do a lot of Monte Carlo applications with very high precision geometry requirements. And so one of the challenges is that unlike discretized PDEs, we have a bunch of branching and discontinuities in effectively our functions. So that poses a real challenge because we have differentiating, a rapidly changing function, of course, doesn't really work. And the second challenge for the mixed precision is that with the detector geometries that we're simulating, there's a order of magnitudes difference that's greater than like single precision. So the detectors are tens of meters large, and we do operations at the micrometer level for doing tiny multiple scattering and so forth. And so that itself means that we can suffer from precision loss just operating on the simulation. And then the other component of the geometric precision requirements is that because we're doing a lot of 1 minus square root of angle, that leads to catastrophic cancellation error unless we're doing pretty precise double precision. So it's definitely challenging for the Monte Carlo detector simulation world.
I completely agree. And there is a paper that me and Jan from our National Lab about the pitfalls of AD. So we're very well aware of all those concerns. And I agree. One thing that during this work I was considering about this control flow divergence, right? Just by there's so much control flow divergence in the code itself. And also when you introduce an error, it could lead to a control flow divergence. And what analysis you did might not even hold at that point. So one thing was to do kind of like a estimate of expected estimate of the error, and with such and such probability of taking this branch, you have so much error, and such probability of taking the other branch, you have the other kinds of error. That could be one way of addressing it, but it's much more challenging than just straightforward do it. The other way would be if you have the input, let's say, which is going to be run, then even if it takes a particular branch, you're getting the estimate for that branch. So in that sense, if you already know what the inputs are, then you could run these analysis, and it's a dynamic thing. So, but it will only hold for that particular input. You cannot generalize it to the entire application, let's say. So you might want to do like a clustering of the inputs to say, okay, this is a new input that's very similar to the input that we analyzed previously. And so we would use this version of the mixed precision algorithm kind of thing. So, but yeah, I completely understand where you're coming from. And yeah, I would encourage you to take a look at that paper too. And it's on my Scholar page. It's about pitfalls of AD. If anyone is really looking to use AD for mixed precision analysis, we have like a long list of problems with that too. But I think there's a lot of work done by Billy Moses as part of the enzyme framework. And I believe he has some work on the error analysis as part of enzyme too. That's another area of work that's happening. It's pretty interesting.
All right, thank you.
Thank you.
Thanks. Any more questions to Harshitha?
I have a question, actually.
Yeah, please go ahead.
So that's a question from the point of view of somebody actually working on CLED.
Oh, okay.
So I've been I recently looked into one thing in error estimation. So I was fixing something related to nested function calls, essentially. And I realized that we don't actually take into account that some built-in functions can have some error to them. So, for example, if a function is user provided, then we generate this pullback, and we also propagate this final error to the function, to the pullback. But if that's some basic math function, then we don't really account for that. So, and I wasn't even sure how to fix that, because as far as I'm concerned, there is no like strict requirement for the precision of such functions. That's the first thing. And the second thing, does that even matter? Because I'm not sure that would actually contribute to this error with respect to some specific variable, or would it?
It would,
So
because
would it actually matter for, yeah.
it would matter in the sense that it's part of that reverse mode of, if you think of the chain of operations that are happening, it's one of the operations, right? But although it's a function call into a library, that which is why we don't have a way to generate the derivative code for it. And the only way we can handle that is to provide a user defined pullback function. So the user would actually have to write the pullback function to say that, oh, this is a function call to, let's say, x square or a square root. Here is the pullback function for that. And one would have to write that. And I believe it would be important for the analysis to take into account that consideration. Otherwise, you won't get the right results. Having said all that, one might not necessarily have to write the pullback function. I mean, I did have some derivation which is not published anywhere, and I haven't had time to work on it. Which is that you can have a sampling-based approach to estimate the derivative. So that's another way. If you don't have access to, let's say, the function itself, the library itself, and you actually don't know what it's doing, you could use some sampling methods. And I'm sure there might be a lot of work in the literature. I'm just not aware of it. But sampling-based techniques could also be used to generate the derivative, although it might have much more overhead or compared to an AD technique, but it enables you to come up with derivatives where it's not literally possible to get the derivatives. Hope that answered your question. If you have specific, you can, email me, or we could have a chat with Vasil too.
Sure. I think maybe having a bit more conversation would be very useful, actually, because we wanted to come back to error estimation recently and essentially get it up to date. So
That's good.
so yes, I think this would be very useful. Thank you.
Absolutely. Yeah. Feel free to send an email to me, Vasil, and we can start that conversation. Sounds good.
Thanks. Any more questions? Yes, Vasil, please.
Oh, hello.
I just want to say thank you for coming and talking to our audience. I wanted to touch base a little bit on what Petro said. It's very difficult to find where to draw the line, because if you say you have like math functions, you also have compiler built-ins and intrinsics, and then which are implemented within the compiler. So it's very difficult to have like a full view of the floating point errors, but getting as close as possible can really help you. And maybe touch a little bit on what was said by, and maybe try to answer your question, how our field is using this. We have two basic branches. One is essentially data analysis, and the other one is simulation. And floating point error analysis matters quite a lot when you have iterative algorithms. When you have like a lot of iteration with a lot of data that kind of like piles up. And for data analysis, I personally haven't seen a lot of these, although we don't systematically check the uncertainties. We don't do uncertainty quantification, for example, when we do likelihood evaluations and so on. When you kind of like do fitting, you don't really take into account the fact that you can have some noise in the floating point operations because the data is noisy anyway. So I think the bigger contributions are somewhere else. But for simulation, I think the boundary conditions are also a problem because, as somebody else mentioned before, we hit discontinuities not only when we do like these operations and functions, but when we travel through materials. Because when you have like a detector, you need to be solving something, and then you have a hit that just goes into different material. And this is where things become very interesting from also theoretical perspective. But you don't have a proper way to do gradient descent or derivative computation because there the boundary is zero. So the integral, you need to integrate before differentiation kind of thing. So I've been thinking about that for quite some time. And there's some recent work on this, which may or may not also impact error estimation. I haven't really thought about that, but just wanted to say a few data points that I was aware of.
Yeah. And I can certainly confirm, I mean, we're working in the event generation, and there we have tried to go to single precision, and we failed miserably because the physics was not correct anymore. I mean, it was just giving wrong results afterwards. So looking into this mixed precision is maybe a good way forward in our case, especially with the GPU market not developing in our favor.
Yep. And it's orders of magnitude that you get performance benefits.
Exactly.
Finding that way analysis is the key.
I saw you showed a factor 8 with mixed precision, and when we go from double to float, we see a factor 2, which is because we have the double amount of processors on the GPU, but
yeah, I believe this has also I don't remember exactly what was their mixed precision algorithm, but I believe this also incorporated the tensor cores and so
that makes sense. Yes. Yeah. Okay, Tess, please.
Yeah, I just wanted to suggest that the factor of 2 speed up. So one of the things is that a lot of the applications here are memory bound rather than compute bound. And so reducing the precision, one of the main benefits that we would see is increasing the bandwidth effectively. And so a factor of 2 would potentially correspond to that rather than an increase in the compute power.
Yep. That's true. And in this particular case, I completely agree. Like memory would be significantly reduced, and that can save you on caches and things like that. But I believe in this case, there were tensor cores with 16-bit precisions and things like that that they could leverage.
Yeah. We find a lot of our kernels are up.
In our case, we're completely compute bound. I mean,
okay. That's good. I mean, if you
it's
can
good. Yes, in some sense, it's good. Yes.
And the register pressure is another important thing to consider,
register,
right? So if you double the number of registers, you can double your occupancy.
Exactly. Yeah. That's it. Yeah. Okay. Any last question to Harshitha before we close the session? Okay, I don't see any. So thank you very much. Very nice talk. And I guess you have a few million more users for your tools. Okay, thanks a lot, and see you all hopefully at the next time at the next Computer Accelerator Forum. Okay, bye everyone.
Bye. Thank you so much. Yep.